You'll have to ignore that. Yeah, today I'm talking about QEpy. So it's quantum espresso in Python. I'll talk about how. Oh, actually, figure out why it's not letting me do that. Okay. Uh, yeah, so the goals of this talk are, so the first I'll discuss the importance of Python and the need of Python-based software in material science, and the difference between material science and chemistry, what the goals are, the different goals. Also, then I'll go into in depth into QEpy, and I'll discuss some workflows, some examples, and how to use QEpy. So first, yeah, so the importance of Python. So all these, so this is NumPy, PyTorch, SciPy, all these are Python-based packages. So these are libraries that are based on Python, and these are the backbone of modern ML and AI workflows. Okay, yeah. So there's a strong demand for powerful but still easy to use Python-based quantum chemistry software. So there are some examples like PySCF and Sci4 for NumPy, these two, and so computational chemistry has made initial strides in this regard. For example, why are these Python packages needed? So I've shown here an example of QChem, which is a conventional, traditional quantum chemistry software, not Python-based, and PySCF. So both of these are doing AIMD. Now, PySCF needs one Python script, no separate inputs, whereas QChem needs a separate .init file for all of these, for each step of AIMD. And you need to run all of them. And whereas for PySCF, you just define a function, you just call it in a for loop, and you get the entire AIMD run. Whereas to get the same data in QChem, it basically becomes an exercise in scripting. So you have to figure out a way of how to read the output files, write your own scripts for that. Whereas in PySCF or any Python-based software, you can get those as Python objects, arrays, and ticks. And so you don't need to worry about the scripting or programming part that much. You can just focus on the data analysis and the quantum chemistry. So, however, so since these are examples from computational chemistry codes, computational material science is lagging behind. What is the what is the difference between computational chemistry and computational material science? I skipped a slide there. Just as a brief aside, this is I hopefully will be a learning experience for all of you. It's also a learning experience for me because it's the first time I'm presenting using Rise. So kind of getting used to how to do things like that, but it's pretty nice. Anyway, so the main difference between computational chemistry and computational material science is the basis sets. So computational chemistry methods use Gaussian type orbitals, and these basis sets are localized and they're focused on the describing the atom centers. And whereas the computational material science uses plane wave basis sets, and these are spread delocalized throughout the simulation cell and depend on the volume of the simulation cell. Also, the computational chemistry methods use an exact potential to describe the system, whereas these material science methods use pseudo potentials in combination with plane wave basis sets to approximate the potential, and essentially they don't consider the core orbitals because you don't need to consider them for all types of calculations. One such method which does computational material science is QuantumEspresso. It's open source, widely validated, extremely versatile. It uses this plane wave pseudo potential framework for accurate and to ensure systematic convergence. Has strong parallel performance, and that's what makes it ideal for large-scale, high-performance computing. Most importantly, QuantumEspresso connects easily to other tools, which is why it's such a natural fit for Python integration. And that's where QEpy comes in. So what is QEpy? So it's a Python package linked with QuantumEspresso. It uses QE as the DFT solver. Also, it handles wave functions, potentials, mixers, and many other tools, and can be integrated with ASE, ML libraries, and workflows. Essentially, the goal is make sure all roads in computational material science lead to QEpy. So QuantumEspresso, and NumPy, and all the Python-based packages. So it's like at the top, and you can use everything. So now how do you use QEpy? Essentially, you just call the main QEpy driver, and you set up the input section, which is very similar to Quantum Espresso. So Quantum Espresso has these control system and these sections, and all of them have these variables which need to be set. QEpy has something similar. So QEpy has, you can set your QE options to dict, and then you can set your own, you can set the same keywords and then set your essentially set up your QE job inside QEpy. And then, yeah, so now, okay, so once we set up our job, let's do density mixing. So using QEpy. First, we need to run QEpy and solve the SCF. So in this case, I'm using like a simple aluminum system, this test case. So you set up your QE options, and then set up initialize the driver, and then run QEpy with, let's say, a simple linear mixing example. So once you have the driver, you can get all the functions that are available. So for example, you can get the density from the QE part. So the underneath layer is still QE. It's just how the data that QE generates and everything is being handled by QEpy. So cost-wise, it's still the cost of QE essentially. So there's no, it doesn't affect the cost of the method essentially. But you can play around with your own. So for example, I'm doing a simple density mixing over here, and I'm running a QE calculation, and I'm getting a converged result. And so if you want to play around with the way you're doing density mixing, you can use QEpy. And the next, so it enables the use of different density mixing schemes. The next example is, so since this is a session on machine learning, say you've developed your own machine learning functional, it's going to solve density functional theory, you need to apply it to computational material science. So QEpy affords a certain amount of flexibility over defining your own density exchange functional. In this example, we'll discuss this example of the Dirac exchange, where you have, so these are the equations for the potential and the XC energy. So we write our own function with the same, using those two equations. You have a Dirac X, which is the functional now, and then you start your QE calculation, and there you go. So this is the SCF cycle. So you get your volume, and then you supply your Dirac exchange functional with the density and the volume, and then you set that as the external potential, and then you do your SCF, and you run your SCF cycle, and you get a converged value. So now you can, in this example, I've used Dirac exchange. You can use any functional. You can, if you design it on the basis of on this framework, you can do any functional. Just define your potential and your exchange energy equations, and there you have it. You can do whatever you want. And that's the overall goal over here, is to make computational material science as flexible as possible.
That's neat. I mean, otherwise you would have had to recompile Quantum Espresso.
Yeah, you have to be like one of the 10 Quantum Espresso developers who know how to do this.
How did you? So have to. How do you do this? I mean, that's
maybe after some years we can help you.
No surgery.
Yes.
So I use the QChem example. So during my PhD, I worked a lot on QChem. So I know it's very difficult to do these things in a Fortran or C++ based software. It's much easier if you use something like Python to do it at the top level. You don't need to go into the nitty-gritty of the code. So you have convert the FT calculation using your model functional. So you define your functional, adds flexibility to the QE calculations. Now, so this is a kind of a callback to the first example that I showed of PySCF and QChem. You can do AIMD using QEpy and ASC. So ASC is the MD part, which is doing the molecular dynamics, and QEpy is doing the ab initio part of the molecular dynamics. So you set up your QEpy and ASC part, you call the necessary modules from ASC and QEpy, and then you read in QE input files. So now you set up both ASC and you set it up to run MD on ASC, and you set up the QE part of the calculation. And now you can use QEpy to extract the wave function information from the ASC dynamics run. So for so this is something that I wrote. It's pretty straightforward. You can use this get wave function option to get the orbital the band information for each step of the ASC MD run, and that can give you lots of useful information. So it's pretty handy. It's pretty neat, and you can also get these things are from ASC, how the potential energy and kinetic energy varies for each step. Along with that, you can get how the orbital overlap, the time dependent orbital overlap varies for each step, how the bands, the phase is changing, the band gap for each step, and these come from the QEpy parts. I haven't shown, so it all takes a little bit of you need to play around with, write your own script to plot this, and that's all it takes. So you need to know what function to call, write your own script, and so I haven't shown the code for this, but I just wrote a small script which plots, which calls in all these quantities and then plots them. And so now you can get all these information, and the reason why this is important is that you can use this to calculate things like non-adiabatic coupling terms. You can get eigenvalues, and all these are important for FSSH calculations. So packages like Libra and a few other packages, which Python-based packages which do FSSH, you can set up your QEpy run to generate the input files for these packages, and then you can run those packs, everything in conjunction, ASC, QEpy, and then your FSSH package. That's pretty neat. That's pretty handy. And so yeah, so in conclusion, QE and QEpy, everything's still the same, except your inputs are minimal. Automation is pretty easy. ML integration is very high for QEpy, and you can use QEpy to extend QE and all of its benefits and powers to any of the wide variety of Python-based packages that are available today. So yeah, it enables broader code interoperability, and so it enables new research in ML-driven electron instruction.
We can start with the questions for Aniket.
I want to know your take on this, but we're going from more complicated like software and having to do inputs, interpret output scripts, Python, right? And now we're in the era of LLMs, NLP, agents. I'm curious to know if you see your quantum chemistry evolving into something where we tell in English the type of calculation we want to do, and we'll have this kind of handle. Is that something that maybe you guys will explore? I'm not sure if it will make sense now, but
yeah, like a chatbot or something.
Kind of. I mean, it's complicated because you have to fine-tune your models, and then you either talk to a provider, paper, token, or whatever. But just your take, do you see a vision like software moving into, instead of scripting language, just pure English?
Yeah, so I think that is in order to do that, you need all these Python-based packages on the layer underneath. So that's surely, that would make the learning barrier, it's not as high. So if you previously to do anything, to implement anything new, you have to learn your own programming. So you have to be like a part-time software engineer, and then on the full-time you're a chemist or a material scientist. But yeah, that would make all that much easier. So any type of new progress will be much faster, I think. So yeah, so for that case, so like to further science, I think that would be very handy.
But the other thing is that if ChatGPT can do QEpy on its own,
Yeah.
maybe.
Yeah.
So we work in my group, we use quantum espresso, and then in combination with Yambo to do response and optical properties. In principle, if somebody were to sit down, they could integrate but QE talks to many other packages that use the output into stuff
with that.
right? I mean, there's also like one-year functions, construction, and in my case, Yambo. So in principle, you could put almost everything under one roof, and Python
Yes.
is just the way to communicate with the
Yeah,
whole thing.
Yeah, so it just makes, that's the main goal. So it's whatever package you need, you connect with QEpy, and then it's pretty simple. Previously, you would have to, and you would still, if you want to do that, you would still have to do some kind of coding. So in this case, you have something which works for QE, and then you write a few lines of code in Python.
So are you considering like sort of expanding
Yeah,
the scope of
It's already
this idea?
so. In fact, Yambo, I think Yambo maybe not among our
Yeah.
already extended QEpy, but we already have things like real-time TDDFT. So it kind of Git pulls all the sub modules in QE and Pythonizes all of those. So they're already Pythonized, but I don't think Yambo is among them. Yambo is not there, and West is not there. So there are some notable modules that are not in QEpy yet.
None of the West people do their own Pythonization.
Maybe they do, so maybe we can hook that up even more easily.
There is a Python version of Yambo, and even on their documentation, they import QEpy. So maybe it works.
They already do QEpy.
So see,
QEpy, not QEpy. All right, they use QEpy.
so maybe it's other guys.
I
It might already be there for you.
That's super interesting.
Wow. All right. So the world knows more about QEpy than us, than we coded it.
Amazing.
Any more questions?
Does the code has already knowledge as you said that
QEpy?
Yeah.
That's what. So I'm working on. I think it's more or less done. It's interfacing with this Libra. So it's basically what I showed you. It just generates the Libra input files and then runs through Libra, and I think it's nearly done. So we're working on that.